Yeah, welcome back. And today I just decided to do things slightly differently. I decided to be presenting a paper, and these will be accompanied by other sets of papers later in the future. But I wanted to present a paper which I found particularly interesting. And it is maybe not the mainstream how people do reinforcement learning, but it is a very important and very interesting finding, which, from my opinion, is extremely important and not a lot of people are trying to focus on that yet. There has been focus on this, of course, but I really found this paper very interesting. So, I mean, even from the title, if we just look at the title, you would find the title a bit interesting and provocative in a sense. So it says that simple random search. So if we just do simple random search in the parameter space, this paper will be about that. It is actually a competitive approach to reinforcement learning. So you know all the stuff we do about reinforcement learning. If you looked at the other lecture, if you looked at the other lecture, and you saw this policy gradients and stuff like that, it turns out that this paper says that random search is as good or competitive to these types of algorithms. So this paper is from Horia Mania, Aurelia Guy, and Benjamin Recht. So sorry if I pronounced the names of the authors wrong. But I really like a lot the blogs that are done by Benjamin Recht, and I learned a lot from them. And I think the preceding these blogs were this kind of like this type of work, and it's really interesting to look into this paper in a bit more details and try to learn something from it, rather than just following the maybe the hype in just doing more and more deep RL and more deep RL and bigger networks and go to 160 billion parameters or something like that. So the paper starts by saying that a common belief in model-free reinforcement learning. So you remember model-free reinforcement learning. If you recall what we discussed in the other lecture about solution methods for reinforcement learning, we said that reinforcement learning solvers can be either model-free solvers or model-based solvers. Towards the end, this paper argues that model-based solvers are actually better than model-free solvers. But then it says that a common belief that model-free reinforcement learning is that methods based on random search in the parameter space. So what I'm going to do is I'm going to search randomly in the parameter space. They say that this is not a competitive approach. What this paper is trying to do is it's trying to say, well, that's not true. You can do random search with even linear policies and show state-of-the-art or competitive results on Mujoco environments, which is maybe the most widely used type of simulator in order to test reinforcement learning methods. So they say we dispel such beliefs by introducing a random strategy, a random search method for training static linear policies. And this is interesting because using standard linear policies, you can actually get very competitive performance to state-of-the-art TRPO, for example. And they're dealing with continuous control problems here. And they say they match state-of-the-art sample efficiencies on the benchmark of Mujoco locomotion tasks. Now, very awesomely, the method they propose for random search is at least 15 times more efficient than the fastest competing model-free methods on these benchmarks. And what is really pretty cool is that they are able, because their method is that fast, they are able to actually do a lot of evaluations. So, for example, a lot of papers out there from authors which I will not name, what they end up doing is they either run 3 seeds, 4 seeds, or for example, they do seed picking, you run your method for a number of different seeds and then you pick the best seed. Now, of course, we know that that's not good science, right? So we all know that. And the main reason is not that these authors are bad or anything like that. It's just simply that these methods are extremely computationally intensive, and running 1 or 2 seeds takes forever. So if you want to run 100 seeds, that's even much more time that needs to be spent there. So because their method is much more efficient than other methods, they are able to run their method and evaluate it over 100 seats. And actually, this is very interesting because on these Mujoco tasks, rarely you see such results. And what they are able to say towards the end is that, you know what, like the evaluation we do, or we used to do in 2018, this paper, is actually not so good because the variance is so high. Right, so that's what they try to say here. So our simulations, for example, here, they just say that the simulations highlight a high variability in the performance of these benchmark tasks, suggesting that commonly used estimates of sample efficiency do not adequately evaluate the performance of RL algorithms. All right, that's pretty interesting. So let's see what this paper does and how it does it, and whether these claims are actually valid or not. So one very important, I highlighted some points from the introduction, which I thought they are kind of important to look into. And these points are I think it's kind of like critical. Some of these points are actually very critical. So they say, for example, that model-free methods have not been successfully deployed to control physical systems outside the research domain. And they give some reasons for that. So they say that the methods require too much data, which is absolutely true. So we have a requirement of like too much data. So one, we have like too much data. So that's a problem, all right? So too much data needed, which means it's highly sample intensive to learn something useful. And also, so that's one of the reasons. And also, it's very hard, because of the complexity of the reinforcement learning zoo, it's really hard to choose which algorithm works better for which task. So, like there are harder choices, like what works better. These are all open questions even till today. And why do they work better? We don't really understand these questions very well. And it is difficult to choose what is the best method for a specific task, and many candidate algorithms are difficult to implement and deploy. And that this is also true, especially if you go to deep networks, then things become very messy. Now, in the quest to find methods that are sample efficient, so i.e. methods that need little data, they say that the trend has been to develop more complicated methods, and that is true. I mean, if you even look at, just have a look at deep RL papers. All they're trying to do is like, okay, let's grow the network. Let's put more RNNs there. Let's put more LSTMs there. And see what happens. I mean, this is by no means any reproducible science, let's say. To me, that type of research is a bit confusing, right? Because science is based in its core on reproducibility, and I find it very hard to reproduce these results. So they also mentioned this here. So Ben and his team, they say that this has led, this increasing complexity right there. So this increasing complexity has led to a crisis in reproducibility. So they say here that the increasing complexity, sorry for that. They say that the increasing complexity has led to reproducibility crisis. Okay, and that is true. So that's another problem. And then they also said that recent results suggest that RL methods are not robust to changes in hyperparameters, random seeds, or even different implementations. And yeah, that's absolutely true. I think one of the ICLR papers recently was something called Implementation Matters. And then the authors there tried to show, the effects of these different tricks and these different implementations on, I think, TRPO, PPO, and other RL algorithms. So, we can go maybe through that paper later. But they say that with such fragilities, like given such problems, increased sample complexity, a lack of reproducibility, and a lack of robustness to hyperparameters, random seeds, and different implementations, it's extremely hard to put these systems in the real world, and that's also absolutely true. Okay. Now, they also talk a little bit, I don't want to go into all the details. This paper is on arXiv, you can find it and read it, but I just want to mention the aim of this paper. So they say that the aim of this paper is to try to get the simplest model-free RL method. So we want to try to find the simplest model-free RL method possible that will solve these Mujoco tasks. Because in RL community, Mujoco, which is a kind of like a dynamic simulator, is kind of the whole grail, right? So it is the one where we test all our algorithms on. And what they're trying to say is that, okay, I want to find the simplest model-free method that can solve such benchmarks. Now, one thing which was interesting from Rajeswaran, and again, sorry for pronouncing the name wrong, they have shown that linear policies, so this is a very important realization, we have to note as well. So they have shown that linear policies, so policies that are linear, right? So no neural networks, no deep learning, no stuff like that, can be trained via natural policy gradients, which is not important for us now in this discussion. We'll go back to it in a different lecture when we continue the series on how to solve our algorithms. But then they show that you can obtain competitive results on Mujoco tasks, right? So linear policies can provide competitive results. Mind you, on Mujoco tasks, right? And now that's interesting because now everybody is putting a deep network there, and maybe the question is why, right? Because if you can just get something as good with linear policies, what's the point? Is it that now the community won't follow the hype anymore, and that's not good? I really have no clue. I mean, I do have to say that from my experience, sometimes linear policies were hard to get to work. And they needed, further tuning and stuff, and maybe a neural network might be easier, but it's still not clear. It's not like a clear cut that neural networks do better than linear policies, because as you will see in this paper, they don't actually do that. And then they also have a derivative-free optimization algorithm, which is kind of a random search or a type of random search. We're just gonna try to maximize a function without necessarily computing the gradients. So what they are going to try to do is they're going to try to combine these two ideas. They're going to take a random search from one side, linear policies from other side, propose a very simple RL algorithm, right? And that RL algorithm is going to be, okay, perturb the parameters of the linear controller and then get the reward, and based on that take a direction. And then they're going to test that. That's how simple the idea is. And now, because it's that simple, what you can see, or what they show, is that these results are 15 times more computationally efficient than other techniques out there. And it's very interesting because they say that our findings contradict the common belief that policy gradient techniques, which rely on exploration in the action space, are more sample efficient than methods based on finite differences. And please note that these methods are methods that go back to like 50, 60 years ago. All right, so so far we're building up some anticipation. Great. Now what? So okay, these are the contributions. We don't necessarily need to go through all of them. I'll just kind of briefly survey the paper, and it's online if anybody is interested in reading it. But let's look at the problem setup a little bit more in order to fully understand what is going on here. So what they are interested in is solving a problem of the following form. So they want to maximize with respect to some parameter theta. So we're trying to maximize with respect to some parameter theta. That's the parameter of the policy. In their case, it's the linear controller. Some expectation under some random variable. And that expectation is of a function R. So that's the function R. And that function R is kind of the reward, right? And the xi is kind of all the randomness in the system. So the idea is that now we're gonna have theta, which parameterizes the policy, and the policy is gonna map from Rn to Rp, and then the random variable xi. So this random variable xi that we have here is a random variable that encodes all the randomness in the environment, which includes, for example, the initial state distribution, some stochastic transitions, but not the policy, because they assume a deterministic policy in this work. Now the value R of pi theta of xi is the reward achieved by policy pi theta on one trajectory generated from the system. So this is kind of the RL problem, right? So the RL problem is like, okay, you have some randomness in the transitions and in the initial state, and now you pick a policy, you execute it. After you execute it, you get a reward. Right, so this is exactly this problem. I mean, we wrote it slightly differently, but these are equivalent problems. There isn't much big difference. So they say in general one could use stochastic policy, but our method uses deterministic policy. All right, great. So now what they're going to do is the following. I mean, they're just simply going to do a random search strategy where they're going to change this theta parameter, get different R values, based on that assess which direction they should take, and then take that direction. That's the algorithm they're going to propose. Very simple, very basic. With linear policies, you might be wondering, does it work, does it not work? And as you will see, it actually works pretty well, which is a bit worrying, to be honest. So now, a primitive form of random search simply computes finite differences. So that's exactly what we just said. You know, you perturb theta a little bit, you get different R values, and then you divide by this perturbation, you get an approximation to the gradient, right? Along the random direction, and takes a step along this direction without using a line search. All right. Now, their method, which they call ARS, is based precisely on this simple strategy, right? So the simple strategy is simply, okay, perturb the parameters, get an approximation to the gradient by just, reward values and, just execute that step. So I think that's what they're trying to show in this equation here, right? So in this equation here, what is happening is that, okay, I'm taking my theta parameter, which is what you see here. So that's the theta parameter. And then so I'm taking theta, I am adding to, sorry, this is so this is the first time I'm using the software, and it's a very, new to me. So, right, so then what they're trying to do is they take this theta, and then they just perturb this theta by some eta, and then by some delta, where delta is randomly sampled. And then based on that, they get the rewards, and then based on these rewards, they just subtract the addition and subtraction of eta delta and divide by no. It's really just a simple random search strategy, right? That's how we do random search, and then they're just using it to compute an approximation of the gradient. And then they say here that, okay, you can look elsewhere, but this is actually an unbiased estimator to an approximation of the original objective which we had here. All right. And now based on that, so you run your algorithm. So the algorithm is really simple. What you're going to do is you're going to, compute this pi change. So that's your pi change in the policy. And then you're just going to add eta delta and subtract eta delta as we described before. And then you're going to update the parameters of the policy theta by just basing on these values of the rewards you got at these different policies, which is very similar to applying this idea in that algorithm, right? So it's simple. It's just a random strategy of saying, okay, perturb your policy, get the rewards, and then based on that, compute your new theta value. All right. Good. So now how are we going to carry that to reinforcement learning? Well, it's easy. What they do is they write kind of like a model for RL, but that model is not that is not that different than what was described just now. What they're going to do is they're going to have an RL algorithm, and then you're going to give an oracle, okay, which is kind of the environment really, a pi theta, and then the pi theta will choose its xi value, and then the xi value will then, based on that, and pi theta will get a trajectory from the environment. Then after it gets a trajectory, it will return a reward value, right? So that's what they try to do here. Now please notice what I just described is exactly what the policy gradient method is supposed to do, or what TRPO is supposed to do, or what any RL algorithm is supposed to do. Or in other words, this is the information is analogous for all these algorithms we just described. You always talk to the environment, you get this trace, you get this reward value, and now you have this set of traces, set of reward values, or set of state, action, successor states, and rewards, and now you want to do something with them, right? So policy gradient says, okay, I'm going to look into, policy gradient says, okay, I'm going to look into gradient of that, and now the random strategy is not going to do that, it's just going to do this like zero order method. And then the question is, as they ask rightfully here, the question then is whether one approach is making better use of the information than the other. So how can we evaluate that? Well, we can evaluate that, by different metrics. We can run the policy, try to see whether learning is faster using one method other than the other, and so forth. So now their proposed algorithm let's just look at the algorithm. Again, the algorithm is not that difficult. It's really very simple. So M is kind of like the parameters of the policy. So they say we use M to denote the parameters of the policy, all right? And now what they're going to do, as we said before, they're just going to perturb, they're just going to perturb this M a little bit, get two policies plus eta plus nu delta minus nu delta, as they do here. So that's what they do here. And now, based on that, they get reward values, they sort these reward values, and then they do an update of the M parameters. We're going to go slowly through this, but the overall idea is just very similar to the standard random search. This is not a fancy, so to say, algorithm. It's the simplest algorithm, as they said, is the simplest algorithm one can think of in order to solve a model-free algorithm. Now, you see here version 1 and version 2 of this problem. And the difference between version 1 and version 2 is a state normalizer. So what they're trying to say, and they describe this in later section, they say that the variability in the state components can affect a lot the random search. So what they try to do is just try to normalize it, and the way they try to normalize it is in what they describe here in version 2. All right. Now, before just executing the update step, they also have one more step of like kind of sorting things out, right? So what they do in line 6 is they sort the delta k, and then they take delta k as the kth largest direction, okay, which is the one that gave me kind of the I believe will be the most profitable one. And then I just do the standard update as I did before, where I just update the parameter by the direction of the gradient, so to say, right? And and that's shown in this equation right here. Now, one thing also I wanted to mention here that they also discuss in this paper is this sigma r that they divide by. So as you see here, they don't have just alpha times this, they had divide by sigma r, and they explain why they made that choice later, because the variance in the reward changes a lot across these different iterations, and then what they're gonna try to do is they're gonna try to divide by that in order not to blow up and keep useful updates. And in fact, they show in this example on a humanoid, a humanoid robot, which is like a walking robot from Mujoco, they can show you that the sigma of the rewards you got with respect to iterations varies a lot. So now if you don't divide by that sigma r, then some parts of your updates will be really big, some parts will be really small, and then things won't work very well anymore. And then the last thing is they're going to update the mu j and the sigma j, which is what's used in order to normalize the states. I honestly don't think, maybe this worked best for them, but I honestly don't think this is the only way you can normalize the state. This is also a trick we do in RL all the time, and you can use any of these tricks here as well. All right, so here, section 3.1, they explain why they want to scale by the standard deviation, and as I said here, so they say here, to address the large variation of the difference of the rewards, we scale by the standard deviation. All right, so that's what they're doing really. And now they say that this behavior occurs because perturbations, as we said, because if you change the policy a little bit, then what happens is that a humanoid or a hopper that's hopping correctly, now you change a little bit, now it can start falling, and now there's a lot of variability in your reward. So we need to define by that. So they actually clearly say that this behavior occurs because perturbations of the policy weights at high rewards can cause the humanoid to fall over, right? Yielding large variation in the rewards collected. All right. And we also discussed the normalizing state, and then they say that this is akin to the data whitening, which we use in regression tasks, and that's a very common application we do, or trick we do when we apply machine learning algorithms. So there isn't anything new or fancy here. And then the last one here is whether to stop utilizing the direction or not. That was the ranking I talked about, right? So for example, we propose, so they say here, they propose to order here. So to address these issues, we propose to order decreasingly the perturbation directions according to the max of the r pi jk plus 1 k plus and pi jk minus. And what's the plus minus? It's just the addition and subtraction of this perturbation, and then use only the top b directions, right? So they just want to use the top b directions. All right, good. So right, That's the algorithm. It's very easy, right? So we go back to it here. The algorithm is really simple. All it's doing is just perturbing the parameters of the policy, yeah, getting values of the rewards, ordering them, taking the kind of like the k largest ones of them, and then doing an update, right? There's no gradients, there's no neural networks, there's no deep networks, there's nothing. There's just random search, all right? So now you might say, okay, is this going to work? Or, what's going on here? First of all, let's look at their experiments and understand what is happening. All right. So, first of all, it's important to note that they ran their experiments on the standard benchmarks that any one of us doing reinforcement learning runs. So there isn't any changes to the environment, any tricks made here or there. There's just the same settings, maybe even less tricks than others do. But they use the hopper, from Mujoco, the walker, the ant, the humanoid, and swimmer as well, I think. And now, there isn't anything different than other methods. It's just running, their algorithm on these Mujoco tasks, and also running the other algorithms to benchmark and baseline. So they did a lot of comparisons, but I'm really, really very interested to start talking about this table 1, right? So table 1 result. So on table 1, you have the task, as we said. So there's the swimmer, the hopper, the half cheetah, the walker, the ant, and the humanoid, right? So all these are very standard benchmark from Mujoco. And now what they have is a threshold, right? So this is the threshold of reward that you would like this system to reach. So for example, you want the swimmer to reach 325 rewards. You want the hopper 3,120 rewards. And now here they have the average number of episodes to reach that reward threshold. So what they're measuring now is, okay, how many episodes, how many interactions the agent has to do with the environment, right? Such that it reaches that specific threshold, okay? So you would expect that a good algorithm will reach that threshold in lower, episodes in order to reach that threshold, okay? So they say that they compare their method, ARC version 1 and version 2, against NG, which is natural gradient, also very fancy algorithm we use, TRPO, which is maybe the most famous one from Berkeley, I believe, if I'm not mistaken, on Mujoco locomotion tasks. And these Mujoco locomotion tasks are what we see here. And what they show is the average number of episodes required to achieve a pre-specified threshold. And they average that over 3 seats. Okay. Now what is very interesting to see already is that if you look at these results, you can see in the swimmer case, for instance, their method is capable of reaching this 325 and maybe 100 episodes for V1, V1T, 427 for V2, V2T. And now what I'm particularly interested in is like the SOTA, right? Like it's the most important algorithm out there, and that's TRPO. And what you can see here is NA, what's written NA. And what is NA? NA is saying that the method did not reach the reward threshold. We just were not able to reach that threshold. So on swimmer, all right, to reach a threshold of 325 rewards, a linear policy, right, a linear policy with random search was able to achieve that, while TRPO with neural networks and policy updates and actor critics and whatever in there was not. Okay. Now, similarly, you would see with Hopper, right? Like with Hopper, they were able to achieve that with VT2 at 1,973, while the others, they went to, what is that, 10,000? Yeah, that's 10,000. And you would see that similarly on all these other scenarios. Now, of course, by no means this is like a state of the art. They're not claiming that this is state of the art. They're just claiming that look, if I use the information you give me in a much smarter, I don't know if it's smarter, in a better way, by just doing random search, I can actually get very competitive results to state-of-the-art algorithms. That's the only claim they do. And in fact, you can see here that the claim is true because on a humanoid, they're not like state-of-the-art, right? But on the others, they are state-of-the-art, which is interesting because now a random search strategy with a linear policy is capable of solving this. So yeah, no deep networks, no nothing like that. So that's one set of experiments which I found particularly interesting and cool. And of course, here they report some learning curves as well, showing that these results are cool that they got. And now, in another set of experiments, right? What they're doing now is asking a slightly different question. So they're saying, okay, I'm gonna give all the algorithms the same number of time steps to run, all right? But now I'm gonna ask which algorithm is gonna attain a maximum average reward after this number of time steps. So for example, they said, okay, in swimmer, I'm gonna go 10 to the power 6. ARS, remember, is their method. So, sorry, here, ARS is their method, right? So that's their technique. And PPO, proximal policy optimization, A to C, actor critic, TRPO, trust region policy optimization, and CEM, I honestly forgot what it stands for. I am sure I read it in the paper, they mentioned it here. So what was CEM? Oh, cross entropy method. So CEM was called cross entropy method, yes. And now what you can see, for example, in swimmer, okay, they get a higher maximum average reward than the other methods, PPO, A to C, CEM, and so on. Of course, this does not necessarily hold across the board. For example, in Walker, they only get 894, but TRPO gets almost 1,000. But funnily, in half cheetah, after 10 to the power 6 step, their method, random search linear policies, gets about 2,345 rewards, while TRPO gets 0, and CEM gets a minus 100. And A to C and PPO get 1,000 and 1,900 respectively. So they can conclude that from table 2, it shows that ARC surpasses these 4 methods on the swimmer, hopper, half cheetah. On the walker task, PPO achieves a higher average maximum, while ARS achieves a similar reward to A to C, CEM, and TRPO. All right. So in 2 experiments, they're either very competitive against state of the art, or they are state of the art. And back then, I think that's 2018. But remember, this is just linear. I mean, I want to keep stating this. This is just linear policies with random search. All right. So again, here you see a similar trend of results. But now, for example, you can see that the other methods can potentially start doing kind of favorably, if not better, by increasing the number of time steps. And now here in this experiment, what they do, which is also, I found it very interesting, is they say, okay, again, I have a threshold, I want to reach. And now I want to see how much steps, it will take me to hit that threshold over ARS, evolutionary strategies, and TRPO. And it's funny because they are able, in swimmer, for example, to reduce from 10 to the power 6 to 10 to the power 4. And in half cheetah, from 510 to the 6 to 510 to the power 5. So again, I mean, I personally find these results pretty impressive and pretty cool because of the simplicity of the algorithm. The algorithm they have can actually allow you to understand whether your method is working or not, because it's very simple. You can run 100 seeds and you can understand the variance in that algorithm, which rarely anybody does. And that's what they try to do here, right? What they're trying to show us here is that, okay, we are going to have variances, okay? So whatever we're doing by just saying, okay, on these 3 random seeds, we are doing fantastically well. Oh, so what? Like, really, so what? Like here we have this algorithm, all right? And they are clearly showing that if I run it for 100 random seeds, the variance is not that small, is it? So essentially this idea of like, okay, let's report 3 random seeds, or let's do seed picking and stuff, this is just not good. So people should stop doing that. All right. And then they also evaluate kind of the sensitivity to the hyperparameters, and they also show some very interesting results. So I really think this paper is worth a read. Of course, I'm skipping across a lot of things, but I'm just giving you why I found this paper very exciting and very interesting. Now this is very very funny. So they just continued running their method, right? So it's just continued running their method. And then they started achieving very, very high rewards. I mean, they even clearly say here that in particular for the humanoid V1 and Walker 2D V1, ARS found policies that achieve significantly higher rewards than other results we encountered in literature, right? So random search with a linear policy was able to achieve state-of-the-art SOTA results. Yeah. And these are some of the results they reported in table 5. So of course I do not know, what's the, if we have some better numbers today, but this was in 2018, and then these results were I think pretty cool, and people should start paying attention, including myself and the teams I work with and so forth. All right. So I'm not going to go into LQRs for now, but I just want to finalize this relatively short video by just reflecting upon some of the conclusions the authors got here, which I think are very, very important conclusions. So first of all, they said that basic random search could be used to train linear policies that achieve state-of-the-art sample efficiencies on Mujoco locomotion tasks. Who would have thought that's true? So they actually show that basic random search with a linear policy can achieve state-of-the-art results. And now they showed that linear policies match the performance of complex neural networks and can be found through a simple algorithm. And I'm very ecstatic and happy that the authors mentioned this, because there is an obsession with deep learning in the community that has to end. It's a good tool, but it's not. We shouldn't put it everywhere. Okay. So these authors, clearly show that we can actually get an excellent performance with a linear policy. All right. And what is very cool is they are able to do extensive sensitivity study, because their algorithm is, very fast, and very easy to run. So they can do that. And they say that our method achieves state-of-the-art performance in logical locomotion when hyperparameters and random seeds are varied. All right. Now this is important what they say here. Our results emphasize the high variance intrinsic to the training of policies for Mujoco RL tasks. Yeah. So they say that, look, there's a big variance here. Be careful about the variance. There's a big variance here. And now what they say, and I fully agree with that, it is not clear what is gained by evaluating RL algorithms on only a small number of random seeds, as is common in the RL literature. And that is true. Anytime we evaluate our models, we take, 2 seeds, 3 seeds, and so on. But they have shown that there's a big variance across the results. So what's the point? What is the point? Why are we doing that? Like, are we gonna, what is it that we're trying to achieve? Are we trying to solve these problems? If we are, we have to listen and try to do better. And then, though many RL researchers are concerned about minimizing sample complexity, it does not make sense to optimize the running time of an algorithm on a single instance. So, you fix the seed, you fix the hyperparameters, you fix the environment, and then you try to do better there, right? But why is that a good idea? It's interesting to ask that question. I'm not sure why that's a good idea. And they give why they think it's not a good idea. Now, at the end, I would like to say, or reiterate what the authors said in their conclusion. So they said, in light of these issues and our empirical results, we make several suggestions for future work. And I think that's something for the community to learn from, including ourselves and everybody else, because I think these are very, very important points and problems that are mentioned by the authors. 1, simple baselines should be established before moving to more complex and benchmarks and methods. They propose to use LQR as a reasonable baseline, as this task is very well understood. When the model is known, instances can be generated with a variety of different levels of difficulty and little overhead. Well, that's an awesome suggestion, but then I might ask, can we publish if we just focus on an LQR? That's something you might ask. And it turns out, yes, you can. There has been a nice thread recently, I think it started a couple of years ago, where authors are trying to analyze and understand the regrets in linear quadratic regulators, if you want to train it from data. And these works are fantastic, and yes, they can get accepted. Now, when games in physics simulator are used for evaluation, separate problem instances should be used for tuning and evaluation of RL methods. I mean, I'm a bit smirking here because it's trivial, isn't it? But we don't do that. I mean, I think they they reflect that that's an important thing. Like we should have a separate instance to test on than what we're tuning on, and running on. And finally, a large random seeds should be used. And this is also important. We need to have a lot of random seeds. Why? Because of the variance. Like picking one seed. Don't do that. And then they say rather than trying to develop algorithms which are applicable to many different classes of problems, it might be better to focus on specific problems of interest and find targeted solutions. And more emphasis should be put on the development of model-based algorithms. And I'm very happy that the authors mentioned this because I feel vindicated. I'm a pro model-based RL solver guy, and I really think this is the right way to do reinforcement learning from my point of view. And a model-based RL can solve some of these problems. But again, as they said, we shouldn't make the same mistakes we made in model-free and model-based. I.e., we should start by having simple benchmarks, getting them to work, trying to understand how they work before we go and, unfortunately, maybe it's too late because people are already putting a deep network in an RNN and an LSTM and all that stuff in there, and, just let's get it to run, let's get it to work. And don't get me wrong, fantastic engineering, fantastic work, but at the same time, we're not really understanding, what's going on there. And all I'm trying to say is that I think in the future we might have a paper popping up like this, and saying the XXX is better than model-based RL with deep networks or something. So, so it's really important to understand what we're doing and how we're doing it before just moving in one direction. So so this is the paper, and I highly recommend reading this paper. It's called what was it? Simple random search provides a competitive approach to reinforcement learning. So I also recommend following Benjamin Recht, who's an awesome, amazing, fantastic researcher with a lot of cool work and cool blogs and a lot of cool stuff happening there. But I think it's worth reading, and especially maybe for newcomers to reinforcement learning. It is important not to maybe follow the hype, right? But to try to understand the important questions to answer. And this paper, I think, asks and provides some open questions that need to be answered. And it's pretty interesting. So I mean, maybe this is going to be a controversial topic. But I really thought it's important to highlight on this. It's been late talking about this. I wanted to discuss this a long time ago after I read this paper, but I have not had the chance to do that yet, so I just did it today. But I mean, please do feel free to read this paper and let me know in the comments what you think about what has been discussed in this paper. I mean, please note that this has spun some big attention, maybe not big enough, but some attention towards solving some of these problems. So maybe the main take from this paper I would take is saying that linear policies, I said it maybe 1,000 times by now, but linear policies with random search do better than state-of-the-art methods in Mujoco. So so I leave you with that, and I will be describing maybe other papers in the future, maybe less how to say that, maybe more of a solved solution to these methods rather than problem posings. But I think problem posing papers are extremely important, such as this one. Right, so thanks again for listening and tuning in, and I'll see you later in another paper. Thank you, bye-bye.